Please proceed.
This meeting is being recorded.
Okay. So, dear colleagues, students, and researchers, uh, I take this opportunity to welcome Professor Yogendra Mishra from Denmark for having a special lecture here at University of West Indies at our campus in St. Augustine, Trinidad and Tobago. And uh, he is a very senior researcher in the field of material science. Many of you may be aware of it, and if not, then we will be discussing it. And so today, on the occasion of World Science Day 2022, as United Nations has declared this year World Science Day as to promote the basic science for sustainable development, and University of West Indies also focus on the various points for the sustainable developments. They have the issues related to the sustainable development on their list, on the priority list. And so we planned this special lecture of Professor Yogendra Mishra at here at University of West Indies. Yeah, Professor Mishra, you're saying something?
I would, it is not allowing me, I have to grant some access, so I will quit and join again in a minute, in a second.
Okay,
Yeah?
okay. So I will start again. Yeah, okay. So welcome once again, Professor Mishra. I hope that I should continue. Yeah, we are able to see your screen. Let me briefly tell you for the new guest here about the University of West Indies. We have 4 campuses. Our campus is located at St. Augustine in Trinidad and Tobago. And we have in our department, which is Department of Physics in Faculty of Science and Technology, we have 11 academics uh, and other staff. And we have the courses like BSc, MSc, MPhil, PhD, special degrees like in biomedical physics, BSc and MSc, and renewable energy technology, which is MSc. And the basic aim for running these courses, especially like renewable energy technology and biomedical physics, is to provide the manpower for the coming industry related to biomedical and renewable energy in Caribbean region. So as we see, coming to the topic, which is the theme of today's lecture by Professor Mishra from Denmark, we see in our life, in day-to-day life, that material science has made much progress in last 30 years, particularly in last 20 years. Even when we were in school, we were not aware that the technology will be so advanced, like the display technologies or sensor or photovoltaics and whatever, or the technology related to transport or whatever we see in our day-to-day life. So when we see the research related to material science, these efforts are, we should give appreciation to the researchers who are doing the research in basic science, particularly in material science, and then technologists and engineers who took forward the technology to the mankind for the benefits of the mankind. And particularly talking about the nanomaterials, we have yet many things to achieve like in various kind of materials, nanomaterials particularly. They are going to solve many unsolved issues of related to technology. And when we say nanotechnology, when we play with the matter at the small scale, there are many possibilities where we see very very different change in the properties in materials, particularly optical, electrical, or magnetic, or and so on. And so many things are yet to be achieved when we say playing with the matter at small scale. New semiconductors, low cost semiconductor, so many fantastic properties with the semiconductor are yet to come. And keeping this in mind, and the theme related to the United Nations Sustainable Goal, and this year's that World Science Day theme, that is sustainable life, with the basic research for sustainable development. We invited Professor Mishra from University of Southern Denmark to just enlighten us for by his lecture. So let me briefly introduce Professor Mishra here for some researchers, those who do not know him. Professor Yogendra Kumar Mishra is a professor at University of Southern Denmark, which is in Denmark and in the north of Europe. And before this, he worked for many years at Kiel University in Germany. He did habilitation in materials, which as I know, it is a kind of second PhD, although this is not a degree, but yeah, it is a work which researcher carry independently at advanced level, and he got this status. So after that, before this, he got the PhD from Inter-University Accelerator Center, which is a UGC center at and Jawaharlal Nehru University from New Delhi. And he introduced this new special process for the synthesis of tetrapod-based materials at University of Kiel, which has many applications, including in biomedical, in smart materials, and many other. So he will be talking today in detail about this research, that how the manipulation of matter at nanoscale, especially these special kind of structure, how they are going to change the future technology for the benefit of mankind. So I take this opportunity to welcome Professor Yogendra Mishra at University of West Indies. And thank you once again. Thank you.
Yeah, so are you able to hear me?
Yeah, we are.
Yeah, thank you very much, Dr. Pathak. It's my kind privilege and honor to give the talk on the Science Day at University of West Indies. I have heard West Indies mainly due to the cricket, so I'm very happy to now know the science and scientific developments and get associated with. Hopefully, I will be able to visit sometime in future. This has been one of the dream places, and I'm very happy the scientific progress you are making over there. Well, and exactly as you pointed out, it's my pleasure and honor, pointed out that this is a kind of United Nations declared scientific day, and we are very much into the sustainable development goal. We are proud to be the first SDG university from Denmark. And actually, there is a lot of similarity. I will come to the next slide. Here you see the beautiful image here from our campus. This is also a small island, and this is the whatever you see is the water line from the sea dividing the city into two parts. I'm exactly standing somewhere here in this building at this location. So that's our workplace, very beautiful small city. It's a nearly zero CO2 city, so it's a climate neutral city, and we are very proud on that. And here we are working on the smart materials at Mads Claus Institute, University of Southern Denmark. The title of the talk today is Tetrapod-based smart materials for advanced technologies. Well, coming back to the similarity, that Denmark is not very big. You can see that this is also surrounded with a lot of water. You can have, you can imagine some kind of similarity to West Indies as well. You have water around everywhere. And our University of Southern Denmark is not very old, it's fairly very young university, but considering the growth, it has been among the top 20 in the world and the youngest growing university. So we have campuses. This university was basically created by merging different engineering colleges in southern Denmark region. So that's why we have kind of campuses nearly in every cities. This is the main campus in Odense, and here we are having in a kind of Sonderborg. There we have engineering campus where we work with the material science. So it's a very rapidly growing university. We are very, very international. With a lot of students and funding. We have really all programs in English, graduates, postgraduates, and PhDs, and we are collaborating a lot. We are here at this campus with 1,200 students. We are more than around 50 nationalities representing here. Well, at our center, NanoSUIT, Max-Klaus Institute, we are having advanced clean room facility with standard facilities, and also we have a state-of-art facilities like electron beam characterizations and also helium boron microscope characterizations, 3D X-ray tomography, electronics. So we are very, very well equipped. And I'm happy to announce that we are launching a completely new program in material science and engineering here, which will be starting in 2023. So interested students are more than welcome. The good thing about this city is that this city is called Sonderborg is an industry city. We have Danfoss, we have many industries which are known worldwide, and basically we are able to accommodate our students into the industries after their masters, after their bachelors and PhDs. So we are very happy about there is 100% employment going on. Well, that was a little introduction. Now coming back to the topic, as Dinesh pointed out, nanoscale materials, nanotechnology, we all are surrounded with materials starting from, we are made out of materials and we are eating materials. Our life is surrounded with materials. So we have to understand the materials. And in the past, from a lot of ancient times, we have been using nanoscale materials, but in last 3-4 decades, these materials have came to us as a revolutionary material, and the credit goes mainly to the development in the engineering and the characterization technologies. So I'm here giving a new motivation today for 3D nanotechnology, and the motivation is directly behind that. Since 4 to 5 decades, we have been working with nanoscale materials. We know it very well that when the material dimension goes to nanoscale, it's basically the surface which is too much in terms of contribution as compared to the bulk, and then it material behaves completely new as a kind of with exceptional properties. So a lot of nanomaterials have been grown. They have been by different methods, nanowires, nanotubes, bells, particles, whatever. The materials have been understood in terms of properties, physically, chemically, theoretically, experimentally. We are now in this situation that we can even kind of see atom by atom in advanced electron microscopes. So we are at this level. So considering the development in last 3 to 4 decades, we can say that we are in a very good stage of understanding nanoscale materials and their properties and developing them. We also know where these properties could find applications, and we know very well. But question is, can we simply go to the market and buy a product which is built out of the nanoscale materials? There is no straightforward answer, because the challenge is the bridge that this nanoscale size, which is introducing nice properties into the material system, is actually a challenge. How, for example, if you want to make a device out of nanoscale material, for example, nanowire, we have to grow the nanowire, and then we have to go to the clean room and to do the integration process. And that becomes challenging because it involves multiple steps. So agglomeration, nanoparticles, they often agglomerate in some applications and devices. We have a lot of integration challenges. So we came up with the idea to work on this bridge from properties to application, how to translate them in a very simple and easy way. We came up with the idea inside the kitchen that if we could arrange nanoscale materials in this sponge form like we have in the kitchen, then we could use them into a desired manner. They are large material but built out of nanoscale elements. That means that we have the possibility to access the nanoscale features at the large scale, and this could open the door to many applications, including here. This is also a perfect example how material architecture, how the internal material architecture introduce new properties into the material system. You can squeeze it, you can expand it, you can hold the water, you can release it, and still you have access to the surface. Very nice. So this is a dream material, but how to make those materials, that is not very easy task. And again, we can go back and task, I mean, this would be the dream material for application point of view, but how to make, this is the question, open question. One can go back and talk in the same way, like top down and bottom up. Nanotechnology 20 years ago, we were talking 30 years ago, and both processes are very expensive. You take a bulk piece and try to selectively mill it either, or to etch it, and that is going to really kind of take a long time. Are making nanowires and then arranging them together, this is also going to kind of make things complicated, not very easy. So we started for kind of developing a simple process, finding out a simple process to develop these sponge-like materials in effective way. That's what the talk is going to be about. And this is based on a nanostructure called tetrapods. So you are living into the coastal area, probably when you are walking along the water side, you might have seen these four-legged structure, which are tetrapods. And there is a very nice, these structures are there by intention. They are not there just because of mistake. The advantage is that does not matter how you put those structures, they are able to self-assemble in form of a kind of network with a random degree of porosity. And that is giving a much more advantage in terms of reducing the force of the water wave. So we came up with the idea that if we could make nano and micro scale tetrapods in the laboratory, then we could really utilize their self-assembly feature to make them a kind of three-dimensional sponge-like material. And that's what you see the image at the bottom. We have developed a method to grow the zinc oxide tetrapods from large amounts in the micro and tetrapod form. These are used in different types of applications, including development of new materials, energy, catalysis, sensor, composites, and many other directions. So we, during the Corona time, we developed basically, and this is a small team which is working with me. And okay, well, you might be wondering, what is this process about making tetrapods? How does it work? And the answer is, it is not something very complicated. This is a very simple process, which was again developed as a motivation from kitchen. If you forget your food into the oven, and then the food is burning, and after burning, what happens? You see in the oven, the entire basically oven is covered with the black particles. As a normal person, you go and you throw. A nanoscientist is never going to kind of throw, probably he will find it as a new form of carbon nanomaterials, whatever. So in the same approach, I developed a recipe that we take a zinc microparticle and polyvinyl butyrol as a precursor material. We fill into the ceramic crucible, and then we put at high temperature into the oven. due to the high temperature into the oven, this polymer burns. It generates the flame which carries away these particles into the flame. And due to the high flame temperature, these particles are converted into the atomic vapor, which is zinc atomic vapor, and oxygen combines. And then we have growth of zinc oxide micro and nanostructures from the vapor phase. So this is solid vapor solid process. The name of the process is flame transport synthesis, and there are several possibilities. If you apply a substrate on the top, silicon pointing, then you can grow really one-dimensional array of nanostructures. And if you do not apply, then you have the possibility to grow basically micro and nanoscale tetrapods, like you see here. First, we have nucleus. Nucleation is happening. Initially, we have formation of octahedral nuclei, and then we have growth along 4 facets, more or less, because zinc oxide is having a crystal structure of hexagonal woodside with a non-centrosymmetric structures, and the C-axis is the fastest growth axis for energy from energy minimization point of view. So that's how these structures grow. And this is the process here that zinc oxide, you can see when the process is going on, crucible is mounted into the oven at high temperature. And this is how the crucible looks like when the growth is happening. The vapor you see is basically zinc oxide vapor. And after the process is over, we have growth. The white powder you see is micro and nanoscale tetrapods. We carefully harvest and use in desired applications. So the dimension of each arm this is around 1 to 2 micron, and this length goes up to say around 2 to 10 micrometers. So they are micro. I will tell why they are nano as well, but we have the possibility to kind of make them into the nanoscale in different forms. So here you see a typical image of a 3-dimensional assembly of self-assembly nature of these tetrapods. Nanostructures, they assemble themselves like popcorn in the bucket when you go to watch the movie. In the same way, popcorns are able to self-assemble. The same way these tetrapods assemble with high porosity. And well, by changing the parameters into the process, we do have the possibility to tailor the arm aspect ratio. Aspect ratio is basically the width to the length to width actually, and here we can make them much more nano as compared to. So this looks like this is made out of zinc oxide, which is ceramic material. But if you see this powder, this is the kind of behaving like a cotton. You can hold in hand and you can play with it as long as you want. Well, why nano, why micro and nano? The simple answer is here, that when you imagine one arm, probably you imagine that this arm is smooth from bottom to top, but it is not the case. It has a lot of staircase structure, which is adding much more surface to the nano material. And this surface is accessible in a very nice way because of 3-dimensional self-assembly. So that makes these tetrapods rather very, very unique. There is no chemical involved. It's a purely zinc oxide material, but this works very, very well. And then how we make a sponge out of this. So we take this tetrapod material, we fill into the mold powder with well-defined volume, amount we decide, and we go to press up to the defined volume limit. And afterwards we heat the tablet at high temperature, 1150 degrees centigrade for 5 hours. What happens due to the heating, the places where they are touching, they form due to the diffusion, there is a formation of junctions, and we are able to produce these 3-dimensional network tablets, which are made out of zinc oxide material. And what is novelty in these tablets is that all these tablets are having the porosity of around say 95%. So when I say porosity of 95%, that means we basically kind of are talking about 5% weight percentage of material part, the rest is the air. But if we try to fill this with something else, we have access to the surface. These tablets are behaving like rubber-like material, high temperature stable, lightweight, highly porous, and the flexible. So there are many fold of applications of these materials, and that is basically our core expertise. Well, and we have been doing this since last 12 years, growing tetrapods, growing three-dimensional interconnected networks. And that's a small conclusion here. And also, I would like to comment here that due to the C-axis growth, hexagonal woodside crystal structure, zinc oxide is a very robust material in terms of the growth. Doesn't matter if you mix two solutions in your kitchen, you will probably end up with some kind of zinc oxide nanostructures. That's how it is criticized that there is nothing left in zinc oxide to which is not published. There are too many publications, already more than 1 million papers in the title. So people ask the question, what is novel in zinc oxide? And they comment, there is nothing left which has not been done in zinc oxide. And I had the same question, but I started and then I could find out this way to go ahead and to develop new class of three-dimensional material. So if somebody demotivates you, please don't work with zinc oxide. Think about my example, and then you could come up, probably it will motivate you. So that is our core expertise. And then you might wonder that where these materials could be utilized, because whenever you are growing any new material, you should always have in mind what could be the application, what could be the high-end product which could be developed from our materials. If there is no applications, then it is not a sustainable way, a long way in future for the success. So always when you are think of growing a material, always keep in mind that I have to find out some applications. And the same question goes to me. You could ask, where I have been using these tetrapods and using these three-dimensional interconnected networks as flexible ceramic material. So I'll show you some of the application aspects here. Very well, those who are working with zinc oxide or metal oxides or N-type semiconductors, wide bandgap semiconductor, the very first idea goes to use them as a sensor, UV sensor or the light sensor. And basically, sensor you design in a way that you take a nano element, you try to interconnect it, and then you try to either measure electrical current, resistance, impedance, dielectric response, or optical response, whatever, depending upon which material, what property we are targeting, and accordingly we are. So we have a one sensing element, then something which is coming as a signal, and then some external component which is measuring this signal, and any external object touched to the sensing element is going to be reflected as a change in its response, optical, electrical, magnetic, whatever it could be. And we, in this thin film based sensing and the nanowire based sensing, we have a challenge how to integrate, and then we have a not fully accessible surface. We came up with the idea that we design a sensor which is just like a network based sensor, like a slab. And in this, we have a very nice kind of surface accessibility. We can deposit electrodes at the both ends, and then we can easily make a device in a very good way. So we tested this for UV light. We tested this for basically gases, hydrogen. We understood clearly the mechanism that the sensing is mainly due to the increase or decrease in the width of the conduction channels. And then basically some more, we more went to the gases, VOCs, environmental, chemical, and then since 2-3 years, we have been talking about biomedical sensing because this has become very, very relevant. And in that context, these network-based devices become very relevant, because if we talk about a single wire-based nanosensing for cell or viruses, when the virus comes in contact, this is very less area which is coming in touch. But imagine such a network bridge basically viruses will move and across, and then they can come in contact, and it will then give a lot of signals, so the reliability will be higher, and still they could pass through very nicely. So we are now focusing more onto these kind of biomedical sensing. The more properties are bendability because of non-centrosymmetric crystal structure. If you try to bend, then there is a piezo effect. You develop the potential across the edges. So that is something, they are flexible, so one can design the flexible sensors, and this is high temperature stable. So if connected clearly, and then it could be possible to design self-powered sensor. So there is much more scope in the direction of powering and sensing, and still we are trying to learn. So making sensors in the lab is very, very nice. I know which gas I am testing. I measure the response, and I publish, analyze, and publish a nice paper. But what if, can I take my sensor to the airport and it tells what it is sensing? Maybe not, maybe yes. Selectivity is very, very important issue. And there we have to work quite a lot. The good thing about these TED reports is that they are open, hollow, so we can change their surface by other molecules for the better selectivity. That's a good thing about. And the chemical conditions, those who are working with zinc oxide are chemists, you know already that zinc oxide is chemically unstable. It can melt easily into, say, HCl or acetic acid, depending upon the molar concentration, which is deciding how far it is going to melt. And there are a lot of other compatibilities. So we need to really work on selectivity, compatibility, and conditions, etc. So those we have been trying to address by making hybrid multifunctional tetrapods, and also creating tetrapods out of new materials. And over the time, we have published quite a lot, but still we are trying to understand the way. And now we are moving more into the direction of developing platforms where we have integrated the sensing and diagnotherapeutic windows together, combining 1D zinc oxide based platforms. So this is the state of art we are now trying to enter into the field, including against COVID. So that is one direction which is coming up as a promising application of these materials. But this is not the only one. I could spend talking 1 week on sensing aspects, but I would like to give you a flavor from different directions, which could be helpful. Probably you are also from different background. Another field of application is composite engineering. Starting from the frying pan of our kitchen to the airplane wings, we are using composite material. They are polymeric material embedded with different types of micro and nano structures, wires, fibers, and nanoparticles. Often we have a challenge in integrating basically how to make homogeneous dispersion of these nanomaterials, fibers into the composites. And these tetrapods, they have the ability to self-assemble themselves in the form of 3D network. So it does not matter how we handle, they are going to form a 3D network. And in this regard, we have engineered polymer composites a lot. Young's modulus to enable bettability, electrical properties, dielectric constant, thermal conductivity. We have engineered a lot. I could keep on talking hours and the days on those aspects. Not only in just engineering, we could put more functions. We could use them for something more than improving properties. We can use them as a filler element, support element to disperse another molecule of interest. For example, designing a smart composite material. Imagine that if there is a kind of damage propagating on the top of the plane wing, then one can easily go and see with the microscope. But if there is a damage propagating basically inside the plane wing, then in order to find out the damage, you have to damage the composite material. imagine if this damage is reflected as a color change. Often these spiropyran molecules are the sensitive to the kind of any deformation they undergo, a transformation, cis to trans basically, and that is a color change. Mainly, so they can be used as markers to reflect any kind of internal damage. The challenge was how to distribute them uniformly from into the specimen so that they could undergo a change wherever there is a change, there is any damage, because they are chemical molecule. It is a challenge. We choose the tetrapods as a support element. We decorated the tetrapods with spiropyran and then embedded into the PTU matrix just 5%, 8%, and there this PTU composite showed a very nice color change under the impact of light, under the impact of heat, under the impact of force. So this opened a channel to design really smart composite materials. We have been working quite a lot in this direction to engineer different types of material with different properties. And even we are opening the door towards designing thermal storage material, energy materials. We could really engineer the thermal conductivity of paraffin wax and then harvesting this as a kind of interplay of the latent heat into the paraffin wax, and we could harvest this energy to use charge our batteries and charge our to kind of as a heat for our home. So it's going on. And well, not only the hard composite material, we could also go into the soft polymer composite directions that we designed the hydrogel. There are hydrogels. If you cut them with a knife and put them together, they heal together because of chemical reactions over the time. And how fast they heal, this is the question. And here we demonstrated that even after putting 2% of the tetrapods, we could really increase the healing response much faster. So that opened the door into a kind of health applications, engineering applications. That's really composite engineering. A third direction of application which came from nowhere to now market. Basically, we started like a regular researcher. So that's why I always motivate young colleagues, students, PhD students to talk with the people from different disciplines, to different kind of backgrounds, because then we could realize problems in a much better way. This is an example here. We met in a conference with Professor Shukla, a virologist from Chicago, and then he noted down that there are some nanoparticles which have activity against viruses. Why don't we work together? Why don't we find out if these tetrapods could do something against viruses, herpes simplex virus 1, which comes on our face and it goes over the time, basically. And what happens in the general, I'm talking about enveloped virus, herpes simplex virus 1. This is a virus identity which is made out of envelope. Inside you have a main element, gene code, and then virus goes and first into the cell culture medium. It interacts with the cell surface. It goes inside via receptors, and then it multiplies, damages the cell. But if we have our nanostructures into the cell culture medium, then basically these viruses are captured by our tetrapods. That's what we learn. And we found out that the tetrapods capture more viruses if we illuminate them with a UV light. UV light means it has a band gap of 3.37 electron volt. So you create electron hole pairs. Electron goes to the conduction band, and then oxygen is happy to take it and go off. So this creates more oxygen vacancies which are positively charged, and then they are helping in basically more binding. Well, to validate it, we study against virus 2, herpes simplex virus type 2, genital herpes virus, human papilloma virus, adenovirus, and many different kind of viruses. And our motivation kept on increasing that probably we could go to a much higher level. But one question we should ask from ourselves if we are working with nanoscale material, that yes, What about the cytotoxicity, that if our material is cytotoxic, then it is not going to be helpful. So we did detailed cytotoxicity study, and we found that the zinc oxide is quite less cytotoxic in tetrapod form as compared to nanoparticles and zinc chloride. And that motivated us quite a lot to go further. And to make the story short here, we infected mice with genital herpes, and then we treated mice with zinc oxide tetrapods, and we could see that the mice treated with tetrapods survived really long here. So you see images here. This is the genital herpes virus, this is WBC, and this is the tetrapod showing the viral binding. And basically it is giving three functions. First, it binds the viruses. The second, it triggers the cell signal to the WBC, go and catch the virus. And the third, there is a certain amount of zinc release which promotes the cell growth, so the wound healing is much faster. So this led to a US patent. We did animal studies and also human studies under doctors prescribed conditions, and the startup company we opened a startup company in Kiel which just launched a product basically. And something, if you didn't know before, even non-material scientists or biologists, now you know it, that zinc is a very important element for human body. It controls more than 200 metabolic function, and if zinc oxide nanoparticles goes into the body, they are decomposed into the acidic medium. Well, so we have been working in this direction, and I'm very happy that this year we launched this new product, our partner company, that is Affinovir. This is a cream which, if you just apply where the viral infection is, and then the viral infection is gone, and just very fast, and it's not coming back. So this is very reliable, and we are very proud and happy with that one. Well, I can talk on, but I'm not a biologist, I'm a material scientist and responsible for material development. So we kept on exploring opportunities where we could, and together with Harvard University, we decided to do some electrospinning with syringe and the collector, and we could design fibers. So initially we were scared of if we break our machine, so we crushed down the tetrapods, and then we designed this membrane embedded with zinc oxide, and this membrane was used to study the bacterial growth at the root canal in the mice, and we could nicely demonstrate the suppression of bacterial growth at the root canal. And this gave us as a first motivation to study more, as kind of put directly the tetrapods into the kind of machine. And this led us kind of to develop a kind of fiber. This is rose spike network. I will be doing fast. Rose spike network in such a way, what you see in your garden, these are PCL fibers. They are used for wound stitching, and often we are talking about not to develop any further kind of infection along the wound side. So we want to make sure this is antibacterial, antimicrobial, antifungal, and we have nicely demonstrated that these fibers are with zinc oxide. They are antimicrobial and antibacterial and also antiviral as well. So a lot is going on in this direction. These tetrapods in special form loaded with protein have been printed into the kind of band-aid, and then they have been used to release the drug for the wound healing study. So this is really working quite well, and we are very happy about it. And coming to the last part of talk, I will take just Dinesh few more minutes, then I will be coming up close. So we have been so successful that each of the aspect, whatever I told is just maybe 10%. We have worked on, and I keep on talking for month and year. The question arises as a general kind of material science: can we grow tetrapods from other metal oxides or metal by the same approach in a simple manner? Because of so nice properties, the answer is no, because it is the material which decides how it wants to grow mainly. However, we found a way its crystalline structure, vapor condition, which are not identical. Luckily, it's very robust for zinc oxide, but we came up the way that we knew that it is going to, we realized that it is chemically unstable under certain conditions. So we could deposit a new material on the top and we can remove the underneath. And in this way, we decided to use them as a template. And with this way, we could create almost any new material in the three-dimensional interconnected network form. So take this tablet, put any chemical stock you want, nanomaterial solution, carbon nanotube or whatever, one component, two component, three component. Now it is a composite material. And if so multiple functions together, if needed, it kind of underneath zinc oxide can be removed. And then one has basically a new three-dimensional material from a new material. Porosity is now above 98%, and still it is like very kind of rough and tough material, open for many applications. This has given us opportunity to almost any material we can convert in this 3D interconnected network form. This is a PDMS material, which is used as a drug delivery carrier material and to the brain, more or less. And we have nicely demonstrated the assembly of 2D graphene sheets into three-dimensional interconnected network, controlling the electrical conductivity and Young's modulus and many different properties, and they have been used for different applications, starting from medical catheter as an advanced electrode for the battery material. And so coming to the last slide, we are more moving into the chemistry applications, nanoscale materials. Often when we do photocatalysis, water purification with nanoscale materials, we always talk about performance, that my nanomaterial is able to degrade the dye and performing very well. But and we write nice papers, everything. What we do not talk about that if we leave a fingerprint behind into our treated water of our nanomaterial. So believe me, in 1960, if somebody would have said that the plastics could be a problem, nobody would have believed. But now after 60 years, we are talking about plastic as a problem. So we should try to find out the solutions in such a way so that we are not creating a kind of problems. At least we should try to avoid creating problems in future. So when we consider use of nanomaterials into the water like applications or the liquid, we have to think about what could be the consequence after 30-40 years. And in this respect, we came up with an idea that if we use these tetrapods as the backbone and put them on the function, then we are making at least a sure degree that they are not going to increase that much contamination, because we have a future history of the material with us. We can reuse them multiple times and we can analyze. So using the activated carbon nanostructures, we designed a composite, multifunctional composite material, which was able to remove the heavy metal ions, basically based on adsorption of chromium 6 to chromium 3 conversion. And by magnetic nanorods, we demonstrated the removal of a diesel from the water, just simply with the magnet. And actually, we have the possibility to put more functions together: heavy metal ions removal, as well as removal of cationic ions and degradation of dye in a very, very good way. So this our system offers designing new material classes, basically engineering them, their functionalities, making them in large form for many applications. And we have been able to convert these kind of tetrapods almost to any three-dimensional networks as sacrificial template from carbon nanotubes, nitrogen-doped carbon nanotubes, tubular network for supercapacitors, zinc air capacitor, gallium nitride, kind of a sponge as a liquid marble, and boron nitride network as a kind of converter, converting coherent light into a normal light, so converting laser light to the room light. So there is much more kind of empty room at the bottom, which needs to be filled with more material creation, more properties, new materials, new functions, new properties, and new applications. And recently we are going more ahead beyond. We have basically this electrospinning as well, and we are trying to come up with more functional nanomaterials, membranes as smart textiles. That is our major focus. So I would like to come to end up my talk rather than saying a conclusion. I would say as an outlook, because I was also asked the similar question, why you want to work with zinc oxide? There is nothing left, but I could follow. I kept on working and I could follow the development, and I developed an own, which is completely new path. It's completely new materials engineering direction, what is going on, what we developed, and we are very happy about it. So still we were invited to write in review and materials today, and then we digged out what is the potential if you combine defect, shape, and the properties together. And that's our kind of motivation to continue in future. The research today is technology for tomorrow. It's just a matter of time. Materials are the key component for any technology. New material creations and characterizations are the key to new technologies. That's basically the three basic aims we follow. And with this, I would like to come up to the end of my slide. I would like to acknowledge Professor Rainer Adelang, with whom I worked for 12 years at Kiel. This development was started with funding agencies. And then I'm collaborating with researchers from all over the world. That's I really like, and please feel free if you come up with any idea. And I would like to thank my colleagues here at SDU Sonneborg, SDU Denmark, and also funding agencies in Europe and Ministry of External Affairs in Denmark and Eco Network. So they are trying to, and of course, thank you very much, Dr. Pathak, for invitation, and I'm very happy to take any questions. So thank you very much, everyone, for listening to talk. And whatever questions you are having now, no question is a bad question. So I will be happy to take them over, and maybe now or later on. Please, I leave it to you, Dr. Pathak, to go ahead and take the responsibility. Thank you very much.
Thank you, Professor Mishra. And those who joined later, I wish to introduce Professor Mishra again. He works at University of Southern Denmark in the north of Europe. And I'm thankful that he accepted our invitation to talk on this today's World Science Day, the materials and basic science research for sustainable life. And very nicely, he presented for the beginner and advanced stage researcher that how this low cost and environmental friendly material, which is zinc oxide, is going to shape our future, replacing the other toxic materials and other high cost materials for the betterment of mankind. And as we run here at the University of West Indies, the biomedical technology, MSc biomedical technology and BSc special degree as a biomedical technology. So I hope they may have also followed that materials can also be manipulated for the better biomedical applications. And we will be inviting him in future at the University of West Indies for further face-to-face and lecture or maybe some other occasions. And now we can have some questions that if faculty and maybe students or researcher from the worldwide, I saw many people join from Europe and some from India and Pakistan as well. I saw some people from some universities. So if you have some questions, we can take them one by one for some time. You can unmute yourself, and otherwise you can chat also your question there. So yeah, first question we can have Dr. Andy Roger, he is the lecturer here in electronics. Yeah, Dr. Roger, you can talk.
Right. Good morning, everyone. Very nice talk there by Professor. Okay, Professor, could you tell us something about doping zinc oxide and maybe how the band gap, how you engineer the band gap that way to probably enhance optical properties?
So basically, zinc oxide in 100% ideal state has a kind of band gap of 3.37 electron volts. And that means you have band-to-band emission into the UV region. However, doesn't matter how you prepare, you are always left with some oxygen vacancies and some interstitials, and that is leading you basically an exciton emission and then a broad green emission, which is accumulation of all kind of defects basically. It totally depends upon our choice how much band gap engineering we plan to do. You could start from aluminum, you could also use magnesium, and you could also use carbon. So it's totally kind of our interest that what kind of band gap engineering or which type of band gap engineering, which level in the band gap we are the kind of we intend to create the defect, and accordingly we can choose a dopant material. Well, also the band gap is quite complicated in the sense that the double vacancy or the double interstitial, they have a different defect level as compared to the single vacancy or the single interstitial, more or less. So in a line zinc oxide, this defect story is very complicated. In a way, and then we also have to see what kind of properties we are expecting in. So if I could get your exact question for particular applications, we can definitely. Even it is possible to engineer the absorption without doping if you can just kind of tailor some intrinsic defects. It could be crystalline defects, and it could be just zinc interstitials and simply the oxygen vacancies. Some defects can also be even created using the plasmas. Is that answers to your question?
Thank you, Professor. Does it modify the temporal dynamics for excitation and recombination when you dope it?
Oh, definitely. Definitely. If you dope it, then you are going to have the defect states, and this is definitely absorption and accordingly the recombination will. So it could, if you have much more oxygen vacancies, then you can get much more green luminescence as compared to a kind of natural ideal blue.
Okay, thank you. Very interesting.
Yeah.
Thank you, Dr. Andrew. Then we have Dr. Amir from Mercury, that is the university in Pakistan. Dr. Amir, you can unmute yourself.
Yes, thank you very much. So it was a very good talk. And then it is very interesting work. So I have one question that is quite a bit, we were discussing about the defect state, right? So people do that like in a doping of certain kind of ions in zinc oxide to produce some defect. So
Yeah.
my question is, have you tried to generate some defect on the surface, one part of this, and then that defect is actually allowing allowing enhanced absorption, definitely. But have you tried to remove an electron from the uppermost or the highest occupied level of or valence orbital of zinc ion? So in that direction, that photophysics would be changed, that the photo or optical properties would be changed. So have you worked in that direction?
Basically, we have doped them with aluminum, iron, magnesium, nickel, cobalt, and many other elements. Basically, we have done, and we have seen an engineering in terms of the optical absorption and also the band gap engineering we have done. Basically, we have not selectively thought of kind of just removing electron. If you just put the material into the UV light, which is simply kind of, if it is band gap more than that, then you can simply create electron hole pair, and then electron is gone and you have oxygen vacancies. Yeah, so we have
Great.
quite much experience in that direction.
Right, great. Thank you very much.
Thank you. Thank you. So I saw Professor Mishra is already active on answering the questions on the chat. So yeah. So if we have some other question which the people want to ask directly, unmuting themselves, then we will take them. Any further question?
Sir, I have a question.
Dr. Andrew, yeah.
Right. Do you want me to go again, or? All right.
Yeah. You can ask.
One question. Is this material better than silicon for building avalanche photodiode detectors, single photon detectors?
We haven't tried. We have not tried. But this material is a direct band gap semiconductor, so I would not use this as a photo detector. Single.
Oh, okay.
Single photon detector, we have not tried, to be very honest.
And can you convert it to indirect band gap by perhaps doping?
Yes.
I know you can do that with gallium arsenide. So
gallium arsenide doping we have not done. By the way, gallium arsenide is a direct again. However, we could make a material out of silicon tetrapods in the same way.
Yeah, because I know if you dope gallium arsenide above 70%, it goes indirect. So, and gallium arsenide is direct band gap. So I was just wondering whether
it depends. If you dope it with indium, say more than say aluminum gallium arsenide, if you go aluminum above 0.3%, then you start getting the indirect nature. Right.
Okay.
Yeah. So aluminum gallium arsenide, so typical, you remain up to say 0.333, x is equal to 0.33 as a direct, and afterwards you start getting an indirect nature. I mean, there is just the interplay. So before, when you start indium for aluminum from 0, it is a direct, and then over the time, basically above 0.3, you start becoming indirect nature.
But can you do that with zinc oxide as well? That the tetrabond?
We have not tried actually. It is too much. It is very much direct. So
right. Okay.
I have to look into the band structure actually. Honestly, I never thought of making a zinc oxide to be an indirect semiconductor.
Okay. Thank you, Professor.
Yeah, welcome.
Yeah.
Thank you once again, Dr. Andrew. So we have some further question by unmute. Otherwise, I saw Professor Mishra already answered the questions on the chat.
Perthabi was asking, is there a reason why there's step-like regions in the surface? Yes, because of the surface chemistry and due to the high temperature, this is the energy minimization which is going on. And this is not really into very good thermal equilibrium if you take. So just imagine if you heat a specimen at low temperature for a very long time, or if you heat the specimen at very high temperature for a very short time. So that's the second case. So you develop the instabilities at the surface, which leads you to formation of these edges.
Yeah, thank you. Thank you, Professor. Okay, thank you. So if we don't have a further question, I invite Dr. Sharma. Dr. Sharma, are you there?
Yes, I am here.
So, yeah, to take it further. Yeah, thank you. Thank you. Thank you once again, Professor Mishra.
Most welcome. It's my pleasure and honor.
Thank you. Yeah, thank you.
Yeah.
Okay, so first of all, I would like to thank Professor Yogendra Kumar Mishra from the University of Southern Denmark to accept our invitation and invitation for this talk. I was listening to the talk was very wonderful, and I even correlate here. So I'm seeing plenty collaboration possibilities are here, especially let's say in biomedical field. We have one colleague here, Dr. Nikolai Zuzikov. He's working on biomedical applications. So, but he's using radiation. He's studying the effect of radiations on the mammals, etc. Okay, but he probably using some nanomaterials like you suggested. You have used tetrapods and using their antimicrobial and antibacterial property. Further work can be done. Collaboration possibility is definitely there. And then also I am seeing that you have worked in water purification area. Myself is working in the area of microbial fuel cell. So we are looking at wastewater treatment and then electricity generation out of that. So there is also possibility maybe we can collaborate on that area, and we can get your guidance on what type of material we can use over there. So very, very impressive talk. And we have seen you are very active. You have patent, and actually the patent is being utilized in the industry. This is the main thing.
We are very happy about that. We could come up with some kind of, say, a kind of LED application into the market that gives us much more freedom.
Yes, thank you, Prof, for your talk and yours in giving us overview of your work and possibilities of collaboration. So thank you very much. And I also want to thank Dr. Pathak here, Dinesh Pathak here, to arrange such a good talk and create further research culture here in the university and popularize this university outside of the Caribbean region. We are also doing good work here. And
it's a very kind of pleasure and honor, as I said in the beginning, that we never we just knew West Indies only by the cricket. I'm sorry to say that. I would say and I'm very happy that there is a university and there are young brains, and actually we are trying to expand ourselves in terms of campus, say, internationalization, and we are looking more collaborations and more opportunities, and we are looking more to develop basically to sustainable development and continuing education and developing the society. So if you see any kind of scope to say that this is a joint platform where we will be happy to come on board, then definitely why not?
So just for also to add on here, we have also produced Nobel laureate from this region. So this is not only just the sports, etc. We're working hard, and we are proud of that, and we want to make our research more broader. We want to reach outside and do the collaborations. And I saw today in the meeting here, we have person from Dr. Pathak said from Pakistan, from India, and even we also invited person here from the University of Miami and our other campus of University of West Indies from Mona in Jamaica. So all were there. I am thankful for everyone who has attended. So thank you, Professor Mishra, and thank you, colleagues and students who has attended this talk.
Very pleasure and honor, and just an information. I am working with a lot of magazines as in the capacity of editors, and also basically kind of working with a lot of books and publishers and quite active, and also developing joint educational platforms together, because I think this is a real service to the society. So if you see any interface and if you think that I need to be contacted, we can definitely contact, and at least I would be happy to put some opinion on that, and I will be happy to support. That is the only way we can go ahead. Education.
Thank you, Prof, for that offer. We will definitely contact you, and we will utilize your expertise in many areas, because sometimes we need examiners for MPhil and PhD theses, and also we need examiners for our courses.
Totally fine.
We have 5 material science courses here, so we need
Right.
examiners, external examiners to evaluate that courses, how we're doing, whether we are performing well, students are performing well, our standard is up to mark. For that kind of activity, we will definitely seek your guidance and your support.
Totally fine. Totally fine. I will be really happy to help that. Yeah. Okay, great. Then are we done?
I hand over now to Dr. Pathak. Dr. Pathak, if you want to say anything.
Yeah, thank you, Professor Mishra, once again on accepting our invitation on this occasion on the World Science Day. Particularly, it is good that United Nations has put the theme basic science. Otherwise, worldwide we see even in people promote the technology and industry only, but this year theme is very good, promoting the basic science, because as we believe that the technology and ultimately the industry that comes, that is a child of the basic science, but people started from the small lab in the basic as a theme of basic science that went ultimately to technology. So we are highly thankful that very nicely you guided the young researcher here at Caribbean region, and worldwide many people joined from the east side also, India, Pakistan and other I saw. So I'm thankful, and we will be contacting you further for various collaborations and to promote particularly material science at University of West Indies, either at this campus or maybe at other. Thank you once again.
Most welcome. Most welcome. Yeah. Okay, then have a nice day ahead.
Thank
okay.
You.
Bye. Thank you. Bye.